Hey guys, so today we are going to work on calibrating the HP130. I'm still waiting for my boards. I've got all the parts in for the other project I'm working on, which I'll link right here. And so I just thought it'd be a good time to do some calibration of this nice old oscilloscope. So there's several tools that you really want for this sort of thing. First, you want a high voltage probe. This is to check the anode of the CRT, and a good fluke multimeter. It's got all the ceramic fuses and stuff in it that you really want. Some good probes. I really also like these very sharp tip probes because there's not a lot of surface area to accidentally touch something else. These things have a lot of surface area, so you could accidentally short something and really cause a lot of problems. The other thing I really use a lot, let's move this, is this isolation transformer. This is very, very important. And what that does is it isolates the entire test set for you from earth ground, because you really don't want to shock yourself. So you always want to use one of these. There's videos out there on why these work well. Right now I'm not going to do a video on that, but if you'd like to have a video on that, go, ask me and maybe I'll do it. But it's real important to use one of these whenever you're doing especially high voltage stuff off of mains. So there's a lot of energy that can come through here. It's even better to have this on a circuit breaker. And then I use that right onto this power strip right there. And then so all my other test equipment, like my counter and my function generator, then the grounds are isolated from earth. The only time I do ground to earth is when I use my test oscilloscope. Not my device under test, but my test oscilloscope. So this will be the scope we use if we have to take any measurements, when we have to take some measurements, because there's some ripple measurements we'll have to take. So this is the scope will do that. This will be connected to earth ground, but at that time I'll be very, very careful to do this properly. It's real important to have your oscilloscope tied to earth and not float your oscilloscope. So that's another video for another day as well. But so let's go ahead and get started. We'll start by checking all our voltage rails. We'll save the high voltage one, but we'll do the high voltage rails first, okay? Alright, so let's take our voltage rail measurements. As you can see here, this is where my ground is on my fluke multimeter. And I'm going to start, let's see, with the negative 150 volt rail, because all the other voltages come off of the 150 volt rail. One of the nice things about this board is they label which traces are which voltages, so that you can just go through here like this. Let's see, the negative 150 is at minus 147.2, and so 1% of that is plus or minus 4%. So 147.2 is well within 4% of 150. That's something like, let's see, that's going to be 6 volts. So as long as we're within 6 volts of 150, we're in an acceptable range. And at 147.2, that's within an acceptable range. All right, now we'll do the 100 volts because it's the next most important, because the 300 and 585 are derived off of that. So 100.4, okay, I'd say we're okay there. Just saying, don't know for sure. But I'd say we're probably okay. And let's see, the 300 volt one, let's see, where is that? Let's see, 300 volts is right here. And so that is 298.9, 299. That's very much within the 4% tolerance again, and then the 585. Oh, it just turned off. Let's see. Now I expect this to beep at me to let me know Yeah, see, it beeped at me to let me know that it's a very high voltage and I should be extra cautious. So that's 584 volts. So it's a very good regulation after 60 years. Okay, so I'm just going to go through all three of those again to kind of show you. Now this is a very dangerous test to perform. So here's the plus 100. I'm at 2 millivolts per division. You can see that I'm getting maybe 2 millivolts. There's some real low voltage kind of ripple on it, but I'm not as worried about that. So that's the 100 volts. Let's see. Here's the minus 150. You can see that there's a little bit more low voltage ripple on that. But as it settles in and charges up the cap, it's not as much of a problem. So you can see that that's pretty good. I'll short out the cap and the scope that I'm using. Okay, now we'll do the 300 volts. There we go. Once it settles in, we're getting 2 millivolts peak to peak ripple on that, so we're okay there. Alright, now last but certainly not least, I'm having to move my ground clip, is the 585 volts. We'll have to turn down the gain a little bit. We're at 10 millivolts. So again, there's a little bit of low voltage noise ripple going on there, but it is not bad. And you can see we're getting 30 millivolts of ripple or so. We're in perfectly good regulation on all these. After 60 years, those caps are still working perfectly, which is amazing. Alright, so I'm about to test the high voltage cathode. It's the cathode, not the anode. Usually I think they're the anode, but I could be wrong. I'm not a oscilloscope expert per se. I just use them a couple times. I'm using my high voltage probe. Don't do this with any other kind of probe. And so you just go in there, you press it, and it's at 2,562 volts. Which is well within tolerance. It's only off by about 12 volts. So, awesome blossom, man. I mean, as I suspected, this thing is working a treat. No problems whatsoever. Alright, one of the things I want to do is look at the adjust the intensity. So I've made all the adjustments on, and this is part of the high voltage adjustment. I've made all the adjustments. It says to set the intensity knob to 10 o'clock, which it's at, and then adjust it to where you can just barely see the scope trace. So again, know what you're doing before you do this stuff, okay? This is, quite honestly, not my favorite part of this, because I know I'm really close to some high voltage things. I don't want to... Okay. Now, I can just barely see it. So, that's probably a decent adjustment anyway. It's at 10 o'clock. It comes in right around 10 o'clock, so that's probably good enough. Okay, so the next adjustment is to set the astigmatism. And so I'll find it. Yep, here's the astigmatism pot. So see there, it kind of gets too wide. And there it's, you want a circular sharp trace. See, that's too much the other way. You just kind of adjust it to where it's circular and sharp. So that is pretty sharp and circular. You don't want to have it too high of power on your intensity either, because if it is too high of power, you can actually burn a hole in your CRT and it burns off the filament. So you don't want to burn off the filament. I mean, that doesn't get much nicer. Maybe I'll try the astigmatism one more time just to, I mean, that is a super sharp, beautiful point. So, doesn't get much better than that. On to the next thing. Now let's see what that calibration looks like. Isn't that gorgeous? Look at that. It's beautiful. Absolutely gorgeous. Alright, so now we're going to adjust the calibrator. I've put in a 1 kilohertz signal. Here's the same signal that you're seeing on the other scope. It's exactly 1 kilohertz, and I've verified that with my frequency counter, and it's 300 millivolts peak to peak, as you can see here. Okay, and so here we need 6 centimeters of deflection here, so I'm going to adjust R40, I think. Yep, adjust R40 to get 6 units of deflection. So here's R40. So I'm going to make this adjustment. And I also have to change the vertical as well. Oh, maybe too far there. It's getting pretty close. Let's give it just a hair bit more. Am I happy there? Maybe too much. That seems to be almost exactly 6. It's pretty hard to tell, but that's pretty stinking close anyway. We'll call that 300 millivolts. Maybe I'll just give it another little tweak. Let's see. Yeah, I think that's better. Okay, so now we're supposed to set this to cal, or set the vertical sensitivity to cal. I was on 50 millivolts. So set the vertical to cal, and then this should be exactly 6, but see, it's a little more than 6 centimeters of deflection. So we'll go in and adjust R240 to get exactly 6. Where's R240? Alright, so here I am going to adjust R240 to get exactly 6 units of deflection there. It's a little too much. I would say that's exactly 6 units of deflection. I'm pretty stinking close. So there's a little parallax with the lines on this particular scope. So yeah. Alright, well, that's it. Calibrator's calibrated. Cool. Alright, so now we're going to do the balance adjust. I did the procedure in figure 2.2, and so now I'm going to set the vernier all the way counterclockwise and then adjust R20 to bring that trace back to center, hopefully. There it is. And get it as close as we can. It probably won't be perfect here. It's real touchy. There, that's pretty good. And then what else would use? And now it should be stable as the trace is rotated, and it's very stable. It's not perfect, but it's very, 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 very stable though. Didn't go anywhere. Yay! Now, one thing we could do, probably, is go back and forth between the cal and the vernier and try and dial this in a little bit more, go through the operation one more time. So that's kind of what we did in figure 2.2. Now we'll move this. Oh, look. Now when I adjust that vernier, there is no movement at all. Awesome. Just that little adjustment did everything. And so I've set up all the switches and stuff to everything we need to look at, and now we're looking at the calibrated signal, and it says to adjust for exactly 6 centimeters of deflection again. So let's go ahead and do that. And I'm adjusting R40 for exactly 6 centimeters of deflection again. There, that's a little bit better. It was a little bit too big, so that's maybe a little too small now. I'm kind of anal retentive about these things. You know, I don't want to do this a bunch of times, so I try and get it right the first time and not have to do it again. Yeah, so that's probably about right. Pretty stinking close anyway. Okay, now it says to connect a 50 kilohertz square wave to the vertical input. So I've already done that. And adjust the square wave amplitude for 6 to 8 centimeters. I've done that. And then, set to 50 millivolts per centimeter. And there it is. And so, I can't tell. There we go. And adjust for a nice square wave. I'm going to speed up the time base a little bit and see how it's nice rounded square wave. That's not what we want. We want it square. So now I'm going to adjust C12 for a nice square wave. So here's C12. I'm going to try and get that. Now you see there's a little bit of gain on the input there. That's not what we want. See how it's doing that? So it was actually better where it was. So we'll put that like that. That's probably the best square wave we're going to get out of this, unfortunately. Let's see if disconnecting the signal, no, that didn't do anything. Okay, I didn't think it would, but thought it was worth a shot. So we're probably hitting the bandwidth limits of this, because for sure it's much faster on my better scope, so that's probably just the bandwidth limit. Maybe we'll measure that here in a little bit once we have a little more data, but yeah, looking at the scope trace on my other scope, it's actually much faster than that. So I mean, that's still a reasonably good slew rate for the rise, and the fall time's faster, but the rise times, and you know, we are looking at the 50 kilohertz square wave, and this is only rated for 300 kilohertz, but that edge rate's going to be very, 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 very fast. So looks good. Okay, sorry for this not so great shot. We're going to adjust the other amplitude stages and try and square up these square waves. So we'll adjust it for 7 to 8 centimeters of deflection. And then at point 1, we're going to be adjusting C3. And so I had to put it on its side to actually gain access to C1, 2, and 3. So try and make it better without making, oh, that's pretty square right there for the 0.1, and then we'll go up to 1 volt per division. And we'll have to probably readjust our trigger. There it is. Increase the amplitude again. We might have to go, yep, we're going to have to go to the 20 volt range. You don't need it to be that big. Okay, now we're going to adjust C4, which is this guy right here. And that's pretty square. Not too bad. Not as good as I'm going to get it. And then we'll go to 10 volts per division. And we'll crank up the gain again. I don't have a whole lot of amplitude on my function generator. I've only got about 20 volts peak to peak. And that's pretty stinking square, but I will try to make an adjustment. But I'm not sure it's needed. And I'm also not sure notice that I don't have the right thing to adjust this. You really need a non-conductive screwdriver, but I don't have one. I have some very, very short ones, but I don't have one that's really square, as good as I can get it anyway. So just take a look there. Yep, pretty square. It's best I can get it. Okay, so I've already done the horizontal positioning DC balance stuff, so just show you that real quick. They both kind of come in to that center graticule real nice. Switches right back. It's right back there. So now it says to set this to 1 millivolt per division and rotate the vernier, and then go in here and adjust R120. Now, R120 is way down in here. I'm not super stoked to be reaching around in here, honestly. And you know what? This vernier is really close. I mean, it's maybe moving 1/5 of a division or so. I'm not sure it's worth me risking my life over. Yeah, let's give it a shot. Okay, so I'm gonna balance this out to 0 now that it's there. Okay, and we're gonna turn the vernier all the way to the left, so that's moving about 1/5 of a division. Now the danger in this really is heat and voltage. But really, if I keep one hand out of there, see, now that's pretty stinking close. So if we adjust that, it's still moving about 1/5 of division, but it's still really stinking close. So you know what? Oh, I don't know. Maybe I'll give it another shot. I am able to reach it with a short little plastic screwdriver. I am touching one of the tubes, which is a little bit warm. Now just, oh, see, now the see that Vernier is moving a lot now. See, I maladjusted it. Now, should not move much. There. So, alright, so you put it there. See, the DC balance drifts a little bit. I don't understand why. It doesn't surprise me a whole lot, but I don't really understand why. It's hot. The vacuum tube is warm, let me tell you. And that should be... See, it drifted again. Not quite sure why it does that. It's annoying though. Alright, and that's about all the patience I got for it. Oh look, that's even better. Alright, that's all the patience I got for it. So I'm not doing it anymore. It still moves just a little bit, but it's not much. It just has to do with the drift of the vacuum tubes in there. I think the temperature drift. So they're not completely linear over temperature. And so the tubes kind of get warmer and cooler depending on if I walk by or whatever, you know. So I think that's really what's going on. But that's another step down onto the bandwidth. Alright, so the next step is to adjust the horizontal deflection for exactly 8 divisions, or 6 divisions, pardon me. Yeah, 6 centimeters. So we're already got 6 centimeters this way, but now we want 6 centimeters this way, and we're about 1, 2, 3, 4.5 or so. So it says to adjust. What did I put? Is it R144 to get it that way. So let me see where R144 is. Okay, I found it. So I'm going to go in and I'm going to adjust it. I'll try not to touch anything hot, both electrically and physically. And so I'm going to, there we go. Not intensity. Horizontal position. Yeah, so that's pretty close right there, and I haven't hardly done anything. So, you know what? I think I'm happy with that. Now, ain't that something? Well, so it seems like when you're adjusting the horizontal sensitivity, you need a synchronized function generator, and you need 2 function generators, one with the sync and one without. I only have a single function generator. I actually have two, but neither one of them have any sync capability. So I don't quite know how to proceed from here. I'm trying to think of how to make a microcontroller be able to put out a square wave. There's a 50 kilohertz square wave, and there's an 8 kilohertz sine wave that I need. So I'm trying to think about how to use the microcontroller to sync the two. I'm having a hard time with that though, with how to do that. Not impossible, but it might be tough. Anyway, so trying to figure out how to do that. But yeah, that's really all I got. So there you go. Can't proceed much further without having some sort of syncing capability, so got to figure out how to do that. I don't have a synced input, but I'm going to show you what I do see so that we can keep moving on. So this is to adjust this to 2 volts per division. I'm going to adjust it to 1 just because it works a little better on this scope. I'm going to adjust it to half. So I can't quite get it to 2, but I can get it as far as I can. And then we're going to adjust the horizontal to 50 millivolts per. And do you see what I see? I see like a straight line here. So the vertical is going like this, and it's kind of making this kind of light green color. And then the horizontal is going like this. And so this should be like a nice solid beam on this side and a nice solid beam on that side, but it's not because it's underdamped, if I remember right. So there's some overshoot there. So what I'm going to try and do is adjust this C114 and see if I can make it to where those 2 side lines are nice and straight. Now we won't be able to see the actual square wave itself, but I know the straighter I get that, the more into spec it's going to be. So let me try and adjust C114 for that. Let's see if I can locate C114. Okay, I see it there. Okay. So I'm going to adjust this to where hopefully I can see if there is or isn't any overshoot or undershoot. Oh, you know what? That screwdriver's not going to do it. I'm going to have to use my longer screwdriver. Wherever it went to. I know it's here. What did I do with it? Here it is. Okay, so let's try not to short this out on anything. Make the proper adjustment. I have to go in at this at a little bit of an angle, so it's, whoa, I just got shocked, so maybe I'll back off doing that. Got a nice little twinge there. I'm going to give it one more shot, but I'm going to be a lot more careful this time. No, it's just not going to work. Oh boy, so what am I going to do? I'm not even sure. Yeah, I just got an electrical shock. I'm not even sure how. I mean, I don't have it connected to Earth anywhere. So if I just hit one spot, I have no idea how I actually got shocked. So maybe just because I was touching the case too. I know I was touching the case. That was probably it. So and you know what? Sometimes it's just your nerves too. Yeah, see how that's getting a lot nicer and a lot squarer? It's taking some effort to move it, but it is getting better. And that's pretty darn good on the left hand side anyway. The right hand side's still a little messy. Kind of make it even on both sides. That's a lot better than what I started out with. Let me tell you, I didn't show it to you, but it was going off maybe one whole graticule on the right hand side, which is not good. Now one thing I'll probably do, no, I think that's probably pretty good. So we'll just leave it like that. Don't mess with it, yo. So I'm going to adjust C103. Let's see. Alright, until I don't see that stuff anymore. Oh, see, now it's real bad. So I'm going to adjust it down and see now it's nice and square. So now we'll go to 1 volt per division and give the amplifier on the function generator some more gain and turn down the gain just a little bit so we're still at 6 units per division. Well, that's pretty good, but I think I will try and change it just to say that I gave it a shot. We're looking at capacitor 104 this time. So here I am connected to 104. I'm just, see how it's overshooting now? It's real bad, real gnarly. I'm going to bring that in just until I start seeing the gnarly go away as good as I can on both sides. It's not perfectly linear, but it's still pretty good. Okay, now I'm going to go adjust C102 at the 10 volts per division. And I can't quite get all the way there, but I'm going to give it as good a shot as I can. Just don't have all the gain I need to really be able to do that. So, and that's okay. I can still see it. See, now there's undershoot. You see what it looks like there with some undershoot. So I'm going to get it to where there's no undershoot. There's the overshoot. So I'm just going to dial it in until I have 2 straight lines there. Okay, here's the phase shift. It says it should not exceed 1 degree. I haven't done too many lizard patterns in my life, but if you look real closely, maybe you can see on that there's just a very, very small sliver of dead space there. Almost imperceivable. The ellipse is very, very small. Very, very linear. I could try and just see 114 again, but I think I'm going to leave it alone. We got a nice trace here with a 1 kilohertz, 1 kilohertz signal going into it, and I've already made all the adjustments on the front of the scope. So now I'm going to go in. And on step 4, it says adjust R261 to the mechanical center. So I'm going to come in here and do that very carefully again. Right about there's the mechanical center, and then it says to adjust R134 so that there's approximately 1 marker per centimeter. Okay. R134, right? Yep, R134. So that there's 1 marker per centimeter. pretty stinking close. So at 1 millisecond, we should see 1 cycle per. That's pretty stinking close. If you look real closely. Out towards the edges, maybe not. But, so that's that. Now we're going to come in and do more of the fine tune with the R261. Yeah, R261. So we'll be able to fine tune it. So hopefully we can get the outer edges to also be 1 cycle per division. It's not perfect, that's for sure. It's hard to get 10 of these all lined up, that's for sure. And it's even more particularly hard when you're looking at it upside down like I am. You want to open it up just a hair. See what that looks like. Maybe just a hair more. I'd say that did the trick. Alright. So, next thing it says is to put it to 10 milliseconds and reduce the frequency down to 100 hertz. So we'll go ahead and do that. Oh, adjusted it the wrong way. So I'm seeing on my counter exactly 100 hertz, maybe 101, something like that. This, I realize, it's difficult to see, but I'm not sure. Yeah, I probably need to make a small tweak here. And it says to make that tweak with R260. So there's R260. I'll make a very small change. I want to make it smaller. And it's getting hard to see just because it's flashing so much. Now I want to make it wider. I'd say that's pretty good. I don't know that I'll get it much better anyway. So I'd say that's pretty good. And then finally, to put in a 10 hertz signal and set the horizontal to 0.1 second. And put in a 10 hertz signal. This is going to be really hard to adjust. So we're going to go down to 10 hertz. It's going to be hard for me to even know for sure that I'm at 10 hertz or adjust it for 10 hertz anyway. It takes 10 seconds for my counter to see 10 hertz at any decent resolution. So, but it says it's at 10.1 hertz, so I know I'm really close, but pardon me, getting the persistence on there. Yeah, I'm not sure I can see that. It's going to be really hard to use this at this frequency with the naked eye anyway. And it's not like some phosphors where it kind of holds it a little bit. I mean, it's just very quick. Some phosphors will hold the trace and kind of glow a little bit, but this is not one of those CRTs with that kind of phosphor. It probably hadn't been invented yet. So what you do is you get a Polaroid camera and you'd look at this thing with the Polaroid camera and you'd take a picture of it with a real long exposure. And perhaps I could do that with this camera, but I'm not going to waste my time with it, I don't think. Especially at this sweep speed, I don't think anybody's going to be using it down this low personally. Trying to see if I can tell if it's off or not. I mean, it's really close. Maybe if I bump up the intensity. Yeah. It could probably be closed just a little bit. I think I can see it actually. So let me try adjusting R259. Let's see if I can. There's R259. See if I can tell if I'm making it better or worse. That's going to be the tricky thing. I'm just going to turn it just a little bit. And then see if I made it better or worse. It's super hard to tell, that's for sure. I think I made it worse. I think it's too tight now. It's hard to see. Super duper hard to see. I think I'm going the right direction now. Maybe. I think I turned it the wrong direction last time. Yeah, actually, I think that's a little bit better. Now if I do it just a hair bit more. So what I'm doing is I'm looking down here, seeing where I think that trace is starting. I'm looking up here, seeing where I think that trace is starting. Then I'm looking here, making sure it's starting right at this spot. And it is. I'm pretty sure that that's a better adjustment there. It's hard to know for sure without having a good Polaroid camera to look at it, but I think it's better, I think. So I've spent quite a while trying to figure out exactly what the last test is trying to tell me to do, and I think I finally figured it out. I have the blue wire connected to the horizontal input, and then I also have a 500 kilohertz with 600 ohms connected to that same input. So sorry if this is a little blurry. This camera is not real good about being able to focus up close, so it needs about a foot of distance. So working on getting another camera, but just takes a little time. Excuse me. Alright, so once I did that, then I was able to get this nice pretty square wave, horizontal square wave. So let's show you what it looks like. And it's jumping around. I think that has to do with the synchronization of all this stuff. I've gone through and I've tapped all the vacuum tubes and the capacitors that I thought might be causing the problems. I couldn't really find anything. So I'm going to say it's really not a problem for now. So unless I see when I do the final checkout that there's still problems. See, I think it's just the way it's all synced together. So let's go ahead and square this wave up. I've got my screwdriver here. I know what capacitors need tweaking. I'm keeping one hand behind my back so I don't die. and trying to make this as square as possible. That's pretty stinking square right there. There's also a second capacitor here. Let's see if we can see how that changes it. Okay, so that makes it a little more vertical. And then that's a nice beautiful square wave actually, especially considering the bandwidth of the scope. So there's not a whole lot more to do there. Alright, I'd like to give you a little bit more details about how this last test went together. So this blue wire is coming through the red to that 1 microfarad cap there. And then that 1 microfarad, then the input's also being fed with the 500 kilohertz signal, and that's what's giving me this. Oh, say hello, Annie. Hi. And then the vertical input is actually the sweep, and it's being fed off of V206 pin 1. So I just soldered a wire, and it's also using the red wire all the way back to the vertical input. So there you go. That's how the test is set up, and you get this nice looking square wave just like this. Exactly what you want. So I am on step 4-17, step number 15, and I've already adjusted C223. So now I'm moving on to adjust C225, which is the next cap to adjust. And what I'm doing here again is just trying to get them to where they're all starting at the tick line. And actually, because there's more bandwidth on the rising edge, I'm actually going to be looking more at the rising edge side. And that looks like it's perfectly adjusted. And so now it actually has a 1 megahertz adjustment. And now the amplitude shrinks a lot when I did that. Hopefully I can, yep, see I'm getting a good trigger. I'm going to have to increase the intensity and zoom in. And see, it's not even a square wave anymore. It is not a square wave. So what I'm doing is now is I'm looking at each crossing point, 0 crossing, and I'm trying to make sure they're on each grid line. And so now I'm going to adjust C227. So, I think I want this opened up just a little bit, so I gotta turn it in the right direction. If I can. Oh, there it goes. Didn't want to open up. See that? It's really, really sensitive here. So there's I'm gonna open it up some more. Readjust the trigger so that it's a stable trigger. That's pretty stinking close. It's not perfect, but it's pretty stinking close. Maybe one more small shot at it. There you go. I think that's as good as I'm going to get it. So, perfectly adjusted now. Okay, so we made those 2 adjustments. The last thing we need to do is set the horizontal sensitivity to internal sweep times 5 and make sure there's 5 divisions between each one. So this is going to become an even more difficult trigger to get. I'm actually going to lower the frequency to 100 kilohertz. It's just going to make the adjustment that much better. So that's 1 micro, 2 micro, 5 micro, 10 micro. So now we want this to go across 5 divisions, and what I'm looking at here again is that this lines up with this. So the rising time, the rising edges are at the 5 mark, and they're not quite. It needs to be opened up just a little bit. And so I think R164 makes that adjustment. Yep, R164. So what I'm doing is I'm connecting to R164, and I'm gonna hopefully open it. Whoa! See how sensitive that is? Maybe that's where the jumping's been coming. Maybe R144. I'll be sure to try and spray that trim pot with the little de-duster sauce. So now that 100 kilohertz is equal on all 5 divisions. Now we'll go back up to this and see if we can get some indication that it's at least pretty close on the 1 megahertz. This is an incredibly fast signal for this particular scope. And see, it's not quite there. And I think I'd rather have it. It might be because of the bandwidth limitations of the scope. Oh well, it's not on exactly 1 megahertz either. Let's see if I can dial that in a little better. And that's something I got to remember, is every time I change the frequency, is like I got to watch my frequency counter. See, I got a really good frequency counter here, accurate to 7 digits, and it is accurate. I have tested it in a couple of different ways, and I'm pretty confident that it's at least somewhat accurate. Maybe not all the way down to the 7th digit, but I mean, that's pretty damn good right there, honestly. And so if you look at that, I don't know if you can see that, but there is pretty much perfectly 5 divisions. So it's actually working up at 1 megahertz. That horizontal sweep is in freaking incredible. And just so connect 50 kilohertz signal to the horizontal input, which I did. Set sweep time to 1 millisecond, and set sync to external, and adjust for a 10.5 centimeter long trace. Adjust, let's see, where is it? R229. I have no idea where this is at. Oh, okay. So here's R229 sweep length, and I'm going to adjust it for 10.5. Oh, it's very finicky too. So there's 10. Let's just make it to 10.5. It's hard to really know 10.5 because there's only 10 there. And obviously it's very, very touchy. Trying to get it about right. Ah, incredibly touchy. It's probably a little too little. Alright, well that's probably pretty close to 10.5 divisions. It'd be hard to see there, but there's 10 divisions there, and that's probably pretty close. See, it's just jumping around now, so it's pretty close though. So I'm going to call this thing good after having to, this is the second time I called it good now. I might blow it out and try and make these adjustments again, but you guys get the idea of how to do this, hopefully. And so let's do a final check, just make sure the vertical amplifier is working. And it should be. Let's just do a little check. We'll put it on internal trigger. There we go. A little less gain here still. This is a 50 kilohertz signal and it's working pretty well. So just the vertical. That's pretty good, 50 kilohertz. Let's go ahead and put it in a sine wave, see how fast we can really get it before we lose any sort of amplitude. Let's see. Let's lower the frequency a bit. So this is a 5 kilohertz signal. Okay, and then so we're gonna make it bigger and then adjust the Vernier to give us 10 centimeters of deflection. And so now what we're looking for is to get about 70 centimeters of deflection, or sorry, 7 centimeters of deflection, or about 7%. So when we go to back to 50K, we get a little bit of attenuation, but as we scroll this up a little bit and get more and more, we should see it drop off pretty significantly. And so that's probably 8. Well, I'm going to have to go up to, I'm at 200 kilohertz and I'm going to have to go up to the next division. So there's about 200 kilohertz again. And so that's about 8 centimeters of deflection. And then there's about 7 centimeters of deflection. So that's our 6 dB point, and it's right at 485 kilohertz, which is thumbs up, outstanding. I mean, this thing's 60 years old. I mean, literally 60 years old. Well, there you go. A perfectly operating 60-year-old oscilloscope. I haven't changed out one part on it. Maybe some of the jitter issues would go away if I did that, but really it's functional, it's working great. I will probably try and sell it, offer a recal for a little bit of cost if whoever buys it wants to replace the caps. I just don't want to take the time to do that. So it's for sale. I'm not sure quite how much I'm going to ask for it quite yet, but that's the deal. Works great. I love it. It's really good oscilloscope. I just got to get it out of here. It is not fast enough for the majority of stuff I do. It would be really good for like audio guy, somebody doing sound systems and stuff like that, or just want to display the residual patterns and stuff. That's a fun thing to show sometimes too. So I think somebody will pick it up, hopefully for a decent price. But you know, it is pretty old, so I gotta keep that in mind as well. And it's not useful for most applications, so I gotta keep that in mind as well. But you know, it's a great starter scope if somebody's never had a scope before and they want to get into electronics, doing slow speed sort of stuff. It works up to about 500 kilohertz. I mean, it surpasses its own spec by quite a good number. So, and then, you know, if they want it recaled, I have no problem doing that. If you come want to replace all the caps, I just don't want to take the time to do it. I've got too much stuff on my plate, too many things to do, and and the thing's perfectly functional. So it doesn't take long to cal this thing. It took me a little bit to figure out that very last step, but once I figured out how to do it, it was wham bam thank you ma'am, very easy to do. But it's done, it works great. I've done a couple more little tests on it just to make sure it's still working, and really there's nothing wrong with it. I'd use it if I wasn't doing more high-speed stuff. So anyway, that's all I got for this issue. But look what came in the mail. Whoa! We're going on to our next project, which is going to be to actually open this bad boy up and start testing our WWVB receiver. Awesome. I cannot wait to do this. So it's really high on my list. Unfortunately, I've got a lot of other things that are real high on my list too, like my driver's license is about to expire, so I gotta go to the DMV. I'm really looking forward to that one, let me tell you. Anyway, if you like this video, I work really hard on these. Give a big thumbs up, subscribe. You know the drill. So thanks a lot for watching. I hope you enjoyed it. Like I said, I really work hard on these, and I really want you to have a good time, learn a little something. I've been trying to figure out the right format and stuff like that. So it's still a work in progress. If you have suggestions or project ideas, let me know. This is kind of a hobby for mine on my off time. So just let me know. Peace. Okay, one last thing before I go. I want to show you this vacuum tube right here. That thing has some sort of black coating, like a black paint coating all over it. I think that's original to this scope. This is the horizontal input stage, the very first differential input stage. So the vertical one is not like that, but it could have been replaced at some point, but I don't think it has because it's actually HP labeled. So I don't think it has, but I could be wrong too. But this is really cool. I have never seen another vacuum tube like that. So here's a little close-up for you. Isn't that neat? Here's the one. Never seen anything like that. I actually took that one to work a while back and asked some of the graybeards, have you ever seen anything like this? And, these guys are guys that have worked with this sort of equipment in the past. They've been around for a long time. And they're like, no, I've never seen a vacuum tube like that. So for some reason, they needed to not let any light into that first stage on the horizontal. Not quite sure why. But anyway, that's a very cool thing. And if you watch the end of the video, you get to see it too. All right. I'm going to button this thing up and we are done with this guy. Hasta luego.